Okay, let us start with a quick recap. So last time we were looking at this action which is here. So this, when you take this action and you from here you find the Euler-Lagrange equations of motion, you will get the Schrodinger equation. Okay, and the operator small h here is this operator. Okay, and then what we did was we expanded psi like this. So we expanded as the coefficients a n of t and times u n of x, where u n are the eigenfunctions of this operator h. Okay, and then we treated a n as the dynamical variable and imposed the quantization condition by first calculating Pn's. So you have An, and then you calculate the corresponding conjugate momentum Pn. Okay, remember that Pn are conjugate momenta; they are not physical momentum of. They are not physical momentum of anything in this theory. Okay, these are canonical variables, An and Pn, and this turned out to be IH bar An star t. Okay, and then we impose the commutation relation. And if you see this, okay, let me suppress t, you got delta n m. Okay, and this theory upon quantization had a Hamiltonian which is sum of infinite number of harmonic oscillators. Okay, and then let me go to next page, and then we constructed the Fock space, and the states were the following. So you can operate with a string of A daggers on the vacuum. Okay, and that these states are eigenstates of the Hamiltonian. Okay, and I also gave you an exercise to show that if n1 is not equal to n2 and so forth, that none of these ni's are equal, then in that case the state is properly normalized, meaning if you take this inner product, then you get unity. Okay. And I also gave you an exercise to find the normalization of these states. So if A n1 dagger is repeated m1 times, A and capital subscript capital N dagger is repeated m sub capital N times. Okay, then find the normalization. Okay, I hope you did that. It's not difficult. And also we saw that the states are symmetric under interchange of any of these two. Okay. Okay, this is obvious because these are daggers and they commute, so there is no problem. So symmetric under interchange of ns and nt. Okay. So that's the recap of what we did last time. Now let us consider a completely different system, okay, and that system will be not a second quantized theory. That I'm going to look at the first quantized theory, okay. So the system is the following. So look at a system of capital N number of identical particles which are in the potential V of x. Okay. So you have n number of particles, they are all identical, okay, and they all are in the same potential V of x, and also they are non-interacting. Okay, so there is no interaction between these. Now I want to look at this system, and I will show eventually that the system that we were discussing earlier here, okay, this one and this one are equivalent. Okay, so these are equal. I mean, at least as far as this system is concerned, whatever you find here, you would find in the previous description also. Okay, so that is what I the plan. Now, of course, I am still assuming that these particles are non-relativistic and they obey Schrodinger equation. That's the first quantized version. So we need to set up the Hamiltonian of this system, and then we will find out the equations of, write down the equations of motion, and then I want to construct the states in this system. Okay, so that's the plan. So let's begin. So let's label the ith particle in the system. Okay, the coordinates of the ith particle by Ri. Okay, earlier I was using x, but let me use Ri, R subscript I. Okay, and I because I'm so this will be for particle number 1, it will be x comma y comma, so x1 comma y1 comma z1, like this. Okay. Okay, so because these particles are not interacting with each other, the Hamiltonian will be a simple sum. Okay, it will be just the sum of the following terms. So you will have minus h bar square over 2m. So I'm assuming all of them have the same mass because they all are identical. Okay, and the partial derivatives here are in with respect to the ith coordinate. Okay, the coordinate of the ith particle. So V R I. Okay, and then I should sum over all the particles. Okay, or in short, let me write as h equal to h1 plus h2 hn, where n is fixed. Okay, when you are specifying the system, you have to tell me how many particles you have in the system. Okay. Okay, so this is what it is, or maybe probably I should write not capital H but small h. That will make it resemble what we have already done. So h1. Okay, and where the small h is just this. So when I am writing gradient I mean del over del Ri, okay, which is just del over del x I, del over del y I, del over del z I. Okay, sometimes I will use this notation which is nice. Okay. So I hope you understand that when you have, for example, this operator acting on psi wave function, okay, and the wave function will be a function of all these coordinates, r, all of them, r1, r2, r3, rn, okay. And then when you are taking such a partial derivative, you have to differentiate with respect to the coordinates of the ith particle. That's what this symbol means. Okay, so now if I look at the wave function, the wave function will be denoted by this. So I should write psi. It will be a function of the coordinates of each of the particles, right? So r1, r2, and so forth, rn, and of course it will depend on time. Okay. And what will be the equation of motion for this system? Well, equation of motion is the same Schrodinger equation. So you take IH, let me write equation of motion. IH bar, the partial derivative of psi, okay, partial time derivative of psi, and you have t. And what should we have on the right hand side? It should be h psi, right? H of psi. Okay. Note that the Hamiltonian itself is symmetric under interchange of labels I, right? You see, H is this. So if you interchange 1 with n, for example, here, it becomes Hn plus so on and so forth, H1. So it's symmetric. And that is what you should expect, because you are looking at a system of identical particles. So it's symmetric, and since the particles are identical, you know that there are two possibilities. Okay. Namely, if you interchange particle I with j, the wave function either remains the same or picks up a minus sign, depending on whether these particles are bosons or fermions. So here R j R I. Okay, so I have interchange ith and jth particles. So this is one possibility, and other possibility is the minus sign. Okay, so plus is for bosons and minus is for fermions. Okay, that's good. So let's look at now the eigenstates of the Hamiltonian of this theory. Okay, and it's not difficult. So earlier we have encountered this. So if I take this small h, which is the Hamiltonian for particle number 1, okay, and I look at its eigenfunctions, those we were denoting by u of n, right? For a single particle, the eigenfunctions we were denoting by u of n and with energy eigenvalue En. So that's the eigenfunction that we can use to construct the the eigenfunctions of the full Hamiltonian. Okay, and it's easy to see that u n1. Okay, so I'm putting one extra label here, okay, to distinguish between to distinguish it from the eigenstate of particle number 2. So particle number 1 could be, so this wave function un1, which corresponds to particle number 1, okay, could be the second second excited state. This could be the third excited state, okay, and so forth. Let me also indicate the, so these depend on the coordinates. So let me, in fact, I can suppress R1, R2 because it's clear from this too that this is for the second particle. But anyhow, u n subscript n r n. Okay, this will be the eigenstates of the full theory will be product of the eigenfunctions of individual particles. Okay, because that's easy to understand, because your Hamiltonian is just a sum of all the small h. Okay, so when this sum is acting on the product of wave functions that I have shown to you, you can easily see that you will again get an eigenfunction. Okay, so let me act with the Hamiltonian here. Okay, and this is what we are looking for, and let me write it down. Since okay, the above states are eigenstates. Okay, you can easily see if you take, for example, h1, so this term here, and act on this un1, un2, unn, then this will act on this one. It doesn't do anything to these because the coordinate here is r2, and this involves taking derivatives with respect to r1. Okay, so that operator doesn't affect these ones at all. So these, all these pieces, all these terms sit outside this operator, and it is h1 acting on u1 is just e n1 un1. So you get the un1 back because that's an eigenstate, and all these things are anyway there. So you see, this is how you're going to get en1, and then this other guy here h2 will give you en2, and the same, all the same factors back, and similarly for each term, and then you obtain the following. So h acting on un1, un2, un sub n is en1 plus en2, because you are going to generate another term from h2 which will have the same form except for this factor, and similarly this. Okay, so these are the eigenstates. But now these states do not have the symmetry which I was talking about earlier, that the states should be symmetric under interchange of these two with either picking up a plus sign or minus sign. Okay, so for now I want to concentrate only on the system of particles that are bosons, which means I want to pick up the plus sign here. Okay, and clearly there is no such symmetry present here, so we can symmetrize the states. Okay, and then those new states which you construct, they will carry the appropriate symmetry property. Okay, so let me define a state by the following. So UN okay, here N1 R1, and you have all the factors. Let me UN2 R2, UNN Rn. Okay, then I want to have another term in which these two are interchanged. The R1 and R2 are interchanged, and N1 and N2 are the same. Okay, meaning particle number 1. So here the particle number 1 is in the eigenstate UN1, and this one is in state UN2. Now I want to have another term in which you have UN1 R2, UN1 R1. Okay, so the particle number 1 is now in state, sorry, this is the same thing. So that's, what did I do? UN1, UN2 here. Yeah. So R1 is the coordinate which tells about the particle, right? That this is for the particle number 1. So this is saying that the particle number 1 is in the second eigenstate. Okay, second excited state. I mean, if N2 is 2. And this one, particle number 2, is in N1th, how to say? Yeah, N1th eigen state of the Hamiltonian, the small h. Okay, so what we want to do here is we just want to make the state completely symmetric under any interchange. Okay, so let me make it a little bit more clearer. So if, let's say, I want to make this state symmetric under interchange of particle number 1 and 2, and I do not worry about other particles, then I would do the following. Then in that case I will just do UN1 R1. So I am just writing down what was above. R2, UN3 R3, okay, UNN Rn. Okay, and then I will add to this N2 R1. I have interchange R2 and R1, and these pieces, these factors, I keep the same. Okay, if I do so, then I have arranged for a symmetry between R1 R2 interchange, or particle number 1 and particle number 2 interchange. Okay, but we want to symmetrize fully under the interchange of all the particles. So I should do the following. So I should write plus all the permutations of R1, R2, R3, so and so forth up to Rn. Now if you do so, just like here we permuted R1 and R2, so this got permuted like this. Okay. If you add all the possibilities, all the permutations, the state which you are going to get will be fully symmetric. Okay, and there are such n factorial such permutations. So I would divide this state by, I mean this thing I will normalize by dividing by 1 over square root of n factorial. Okay, and this is what I defined to be this. So these are your eigenstates, symmetrized eigenstates of the Hamiltonian. Okay, good. Then so I'll give you a few exercises now. Exercise, check that the states, these eigenstates are normalized. Okay, meaning if you calculate d cube r1, d cube rn, if you do this integral over u star, you get 1. Okay, so I'm suppressing r1 r2 now. Okay, you get 1 if n1 is not equal to n2, if none of these are equal. Okay, so that is one thing you should show. And the second thing that you should show is, or you find out, is the following: find the normalization when, if you have m1 particles in n1 state, sorry, not n1, so the first excited state, right? So the small h has has states u1, u2, u3 and so forth. The n1, n2, n3, they take values 1, 2, 3 like this. So now we are specifying that you have m1 particles which are in the first state, okay, u1, in the u1 state, and you have m2 particles in u2 state and so forth. Okay, and such that your m1 plus m2, they all add up to capital N, because you have total number of particles is fixed to be capital N. So in that case, you find the normalization of the states. Okay, and once you do that, you will realize that the following is true: that if you compare the second quantized state system which we were discussing earlier, before we started this discussion, okay, before we started this discussion of this new system, okay, the second quantized system that we were studying, okay, if you look at these states and compare with the states which we have constructed just now, these ones, where are they? Here, this one for example, okay, and similarly the ones which, you know, where several of them are in the same state, state u1 or u2, and similarly here if you consider these ones, you will see that there is a one-to-one correspondence between the states of this system and the states of that system. Okay. Also, I think I didn't write here, but I should have. maybe I can do it now. Here I would like to add that, let's do here. If you take Hamiltonian and act on this state, you get it's the sum of energies of some of these energies. Okay. So you see that there is a one-to-one correspondence between these states and the states that we have here in this theory. Okay. So if you take this state and this Hamiltonian, you get exactly the same thing as you were getting there, right? Under this Hamiltonian, which is very different, which is Hamiltonian of an infinite number of harmonic oscillators, each with a different frequency. But as far as if you say, okay, this Hamiltonian corresponds to the Hamiltonian of that theory, and this state corresponds to the eigenstate, the states of that theory, then you see there is a one-to-one correspondence. Okay, and the symmetry properties are same under interchange of any two labels. So if you interchange any of the two, it's symmetric, and here also we have constructed the states which are, let me go here, are symmetric under interchange of any of the two. These are normalized, they are normalized. So you can conclude that this system, which is a system of capital N non-interacting bosons, which are all under which are all in the same potential V of x, which are all in the same potential V. Okay, this system is equivalent to a second quantized system. Okay, which is given by an infinite number of harmonic oscillators. Okay, the advantage there is that, though in this case when you want to add one more particle, let's say instead of capital N you want to go to capital N plus 1, your Hamiltonian changes, and you have to construct states differently, but there you don't have to change anything. It's the same thing, you are just exciting more number of oscillators. Okay, so this is the equivalence between these two systems, and I could go further and discuss how different operators are defined in this first quantized theory which we discussed just now, and what are their corresponding operators in the second quantized theory that we discussed earlier. But I would leave it as an exercise for you to do or read some book or other literature. And what I wish to take up next is start looking at relativistic theories. Okay, so I will leave this study of multi-particle system which we undertook here. The reason I undertook was because it makes the step the step of second quantization very easily understandable in the context of a very familiar equation, Schrodinger equation. And this multi-particle system I want to leave now and want to start looking at relativistic field theories. Okay, and then we will quantize them. So the next thing I would do is look at Klein-Gordon theory, okay, at the classical level, and then we will quantize it. So that's the plan for the next video.